Hey everybody, it's Ripley back again. All right, many of you will never see this video, and if you're not going to see this video, I don't know why I'm addressing you, but you might come across it later in your more advanced statistical analysis work. It's called ANOVA, which means analysis, and this thing is terrible today, sorry, analysis, thank God it's my last video, of variance. Now, let me explain what this means. So we've been looking for differences between means of different groups, different populations, different samples, things like that. But we just came off of using chi-squared to deal with issues like independence and issues like goodness of fit. So what we have here is going to be a confluence of all of these ideas of, hey, I want to find some differences, but I don't really know how to do it. All right, so what you will typically see is called a one-way ANOVA. Now I'm going to explain this with an example. ANOVA. All right, so I am a dean of students at a high school. This high school is just going to have sophomores, juniors, and seniors. And I want to know, excuse me, I want to know if there's any differences between the cut rates of kids, whether they're sophomores, juniors, or seniors, the kids who cut school, all right? So in a given semester, what I do is I've got my freshmen, and I've got my sophomores, and I've got my seniors, all right? Seniors, these would be soph, and these are seniors. And I randomly select 5 students from my populations. It's a relatively small school, all right? And we assume that the cut rates at these schools are normally distributed, but, which is a good assumption, right? It's always a good assumption. We got to be careful with that. But, and you may say, well, Ripley, maybe that's not true, but just bear with me for just a sec. We'll talk about assumptions here in a sec. It makes it a lot simpler if we can assume that they come from randomly distributed populations. So 1, 3, just like always, right? 2, 4, 2. Let me just throw this data set up here real quick. 6, 1, 5, 4, and 4. And this data set will be in, I'm going to show you how to use your TI as well. Okay, so anyway, this dean of students wants to know if there's a difference between cut rates in freshmen, sophomore, sophomores, juniors, and seniors. Good Lord, Ripley. I'm sorry, kids. Let's try that again. So soph, and then juniors and seniors. Okay, so again, grabs randomly selected data from each one of the populations, juniors, and then senior. I guess that should be an R in it. Anyway. Now, the question is how do we test this? How do we figure out if there's a difference between the seniors and the rest of the group, or the juniors and the rest of the group, or maybe the sophomores and the juniors are different from the seniors? Well, what we use is called analysis of variance. Now, you may say, well, Ripley, why don't we just do these things pairwise, right? Because if you think about it in like a high school, I could even have freshmen in here too, right? Or I could do from 7th grade on if I've got like a Catholic school where everybody's in the same school together for 6 years. And I want to try these types of things. Well, 2 reasons that we wouldn't just want to do this pairwise. The more factors we have, in other words, the more classes in this case that we have, the greater the complexity is, right? It would take a long time to sort of pairwise analyze everything. The other problem is that we get what's called alpha slippage, and we're not going to get into alpha slippage because it's more of an advanced idea, and we don't want to dig that deep into what ANOVA really is right now. All I'm trying to do is I'm trying to give you an introduction to what it is and how it works. But first things first. What we're going to do, the easiest way to understand this is to simply write the null and the alternative hypothesis to see what we're really testing. All right, the null hypothesis, remember, null hypothesis always contains the equality, right? So we're going to call this parameter 1, parameter 2, and parameter 3, right? So what we're going to say is the null hypothesis is that the average cut rate, or number of cuts in a semester, or whatever, for freshmen is equal to the number of cuts I said freshmen again, I'm sorry, sophomores is equal to juniors is equal to seniors. Now, the alternative hypothesis is a little different. It's alloy. which means at least one inequality. One of these is off. So all that ANOVA checks for is to see if at least one of these things is off. So think of this as entree into being able to discover whether or not we need to take the time to determine if something is off. Because if the null hypothesis is true, why the heck would we spend any more time? Like, okay, sophomores, juniors, and seniors appear to be cutting at the same rate. However, if we get a significant result, then we need to dig down a little bit further into that. All right, so let me tell you what the requirements are. All right, first things first. Of course, it needs to come from something that is approximately a normal distribution. In other words, the populations are approximately normally distributed. There is an argument to be made that cut rates are not normally distributed, but I'm not going to make that right now. We could check that with our normality check that I taught you back in 6.6 or wherever it was. These have to be independent factors. In other words, I can't be both a sophomore and a junior. I can't be both a junior and a senior, etc. All right? You got to be simple random samples, just like always. They can only be categorized in one way. In other words, I can't say like this is sophomores slashed females, right? This is just sophomores. I can only grab one factor at a time, and that's all that I care about. All right? Also, that the populations have approximately the same variance. All right, now that's key. The populations having approximately the same variance is key. So same variance is that assumption has to at least be, and it can be really difficult to check that at times, but you can check it, right? We can check it with confidence intervals, true, to double check it. But this is a big assumption. Now, the question is, what do we use? How do we do this? And the answer is we're going to use what's called an F test, which is the test for the ANOVA test. All right? Now, the F test looks strikingly like the chi-squared test. It's got this right skew. It's always positive, which makes sense. All right? We're dealing with variance. We are literally analyzing variance. Now, let me tell you what the F test is without getting into the mathematics of it, because the mathematics of it is awful. So consider this very much like trying to calculate Pearson's R coefficient by hand. You aren't going to do it. You're always going to use some sort of software. All right? So the F test is a really simple ratio. It's simply the variance between the samples, how much we vary between samples. Now think of these as errors, though, because that's going to be a little bit important here in a sec. Divided by the variance, where is my R? Imagine there's an R in there, or an I in there. Variance within. Now, what is this? What does this mean? All right, so think of variance as error, right? It's the difference between the mean and the actual values. I realize I'm oversimplifying. Please be patient with me for just a sec. In other words, we're looking at variability between each one of the factors. So between sophomores and between each one of the classes, I'll keep it simpler. Between sophomores and juniors and seniors. So it's kind of like we're taking all of the data at once and then cross-comparing all of the differences between sophomores, juniors, sophomores, seniors, juniors, seniors. Now, from a mathematical standpoint, you can probably imagine the headache, right? All right, now, then we have the variance within. Again, just let me plant a seed. Think of variance not as variance in the mathematical computational sense, but as error. If I divide the total variance between all of the samples by the variance within, so now I've got this variance within, right? Now, when I say variance within, that just means the error within each one of the groups. So I would just calculate all these guys. And I use something called the mean squared error, the MSE, or just mean squared. We'll talk about what that is here in just a sec. Excuse me. But if I do that, if I divide out, think of the variance between samples as being the total error in the entire system. It's like it's one big data set, almost. I'm overly simplifying that. I apologize. But then I take that and I divide out the variance within. Then what's left over, right? I'm dividing it out. So think of it like I take 24 and I divide it by 8. Well, this is clearly 3. Well, what does 3 represent? It represents the number that's left over right? After I've pulled out all these 8s. Same thing here. When I divide out the variance within, what I'm left with is the total area, the total error in the system. Now, error, in this case, what I'm talking about is variation. I know variation and error are not the same thing, and I do not want you to take that away from this. But variation is distance away from means, right? So it's kind of okay to talk about it as being error from the mean. That's why we'll talk about something called mean squared error, or MSE. Okay, so, sorry, I got stuff in my pockets. I got to clear the baffles here. All right. Okay, so let me explain how this F test score is calculated, okay? Because it's actually pretty simple. All that I do is, this is the fun part. What I do is I take what's called the mean square error, which is the MSE, for between groups. Let's go error for between. Now, what is this mean square error? What it is it represents the variance between samples. That's all that it is. I simply take that guy. It's another way to say mean squared errors for between. So think of mean squared error as variance, right? But you got to be a little bit careful there, because what I'm really doing is, it's not exactly variance. I'm sorry, I was a little glib when I said that, because I'm not dividing through by that n-1. And the reason why I do that, I'll show you that here in just a sec. I'm going to put a little f right here, and then I take the MSE, I'm lazy, I know, mean squared error for, within groups. And I divide it out. Now you may say, well, wait, Ripley, you just said that this wasn't variance. Well, it isn't, because we don't have to worry about, remember, to find variance, I have to divide through by that n-1, and then to find standard deviation, I take the square root of the whole thing. Go away, sorry. So those just cancel, those n-1s. Like we don't worry about those, because truthfully, they just muddy the waters. Now you may say, all right, what about degrees of freedom? Well, let's talk about degrees of freedom. Degrees of freedom is really easy to compute, but it's kind of important for a couple of reasons. First, there's the degrees of freedom for between, and this is important, and I'll show it. Right now, you're kind of like, what are you doing, Ripley? Well, it's easy. I simply take, in this case, 3 minus 1, which is just the number of groups. All right? And then I take for within. Now, this one's trickier. What I do for within, is I have to take, I'm sorry, I'm choking over here. I take 3, right, which is the number of groups, sophomores, juniors, seniors, and then I have to multiply that times 5 minus 1. So where does 5 minus 1 come from? Well, it comes from these group sizes right here, because I took 5 in each set. So this is going to be 3 times 4, which is 12. All right? Now, again, you do not want to have to go through the process of computing all of this. So, me, being the charitable young man that I am, well, old man, sorry, has done it for you. Let's kick over real quick to, let's get rid of that. I was going to show you guys the true definition, but I figured it just muddied the water. Let's go back over here. So, let's go to stat, and then we're going to edit. And here's where I've got that same data. So this should be exactly the same data that I just put in. Now, the cool thing about this is it's really just one set of keystrokes and it's done. And then we're going to kind of jump back and forth between what the output says versus what we just spoke about. So let's do stat, and we're going to do a test over yonder, and I'm going to go up because it's always the last one, and I'm going to hit enter. And then hopefully you saw that I stored those in, let's see, second L1, comma, second L2, comma, second L3. And now I'm going to hit enter, and then we're going to look back. I'll look back at what we just did for just a sec. All right, so here we go. F, strangely enough, is equal to 1. Now, that's insane. But what we really care about is P. Okay, so the p-value is 0.39656. So we know had we set our p-value at 0.05, there's no way that this thing was going to be significant. We know that for sure. Also, we know that if I were to, I'm going to kick back over here real quick. Let me get big. And I go here. I mean, if I set, let's say that my critical F was right here, then my F value here would have been, 39% of the data would have happened to the right of this, just like how chi-squared works. It works the exact same way. So let me back out of that real quick. Let me kick over here. I've got degrees of freedom, which is 2. Now, just like I said, here's the 2 down here. I don't even have to jump over. Now, the sum of the squares and then the mean squared. So the sum of the squares is just if I were to take the sum of the squares of all of it, so the squares of the differences, and add them up. And then the mean squares is just the average. That's all that it is. It's very simple. Now then I see error, which is kind of frightening, isn't it? Because you see it and it's like, wait, this is the same error message that I get when I will actually take an error, but this is different. Now, for whatever reason, the TI assumes that error for us means within group error. Now notice that the degrees of freedom are 12, the sum of the squares are 39.2, and the mean square is 3.2667. By the way, I just pulled those numbers out of my ear. Now I want you to notice something. This is the reason that F was 1, because the mean squared error for the between groups was 3.27, and the mean squared error for within groups was 2.37, and I always divide those two. All right? Okay, cool. So let's kick back over here, have a quick little discussion about what this means. I'm gonna cheat a little bit, and then we'll talk about how to move forward. Because again, this is just an introduction. In no way should you be worried about like being able. Analysis of variance is really it's the first really kind of high-level statistics that you will do in an advanced statistics course. It's the first thing that you kind of learn because everybody's seen t-tests and c-tests and using p-values, and you understand significance and writing null and alternative hypothesis, things like that. But this is new and different, right? I can analyze a whole bunch of stuff. Like I said, I could have started 7th grade and then 8th grade and then freshman, right? And then done this big old analysis of variance as well. Excuse me. Now, what do we do? There's a question, and I always get asked it. What happens if, say, p is less than 0.01? So when I did when I threw it in my calculator and I get p is less than 0.01, now what do I do? Well, now, since you know that there is a difference, and now you're trying to find it, what you have to do is you start looking at these things pairwise. It's like, okay, what do I do? What should be the move? Well, you can do something called a Bonferroni. This is a Bon, and you're not going to do this. You probably won't. A Bonferroni multiple comparison test. And we're not even going to go into this because you don't need it. Comparison test, unless you do, in which case it's on your instructor to let you know. All right, and basically what that uses is just a t-value in between these samples. All right, so I would say, okay, now I know there's a difference and I need to identify where it's at. So I would take, okay, sophomores, juniors, and then I would use this multiple comparison test, and I would use junior, seniors, and I would just test these things pairwise one at a time. Okay, lastly, the question that students often have when dealing with analysis of variance is, what happens if these sizes right here are unequal? In other words, if we're taking different sample sizes. Well, then the calculation of it becomes horribly onerous. It's a pain in the butt. You end up with very strange degrees of freedom. You don't end up with integer value, or not integer values, but whole number values of degrees of freedom. And all hell breaks loose. But at the end of the day, the calculation itself is still the same. I simply divide the mean squared error for between samples by the mean squared error within samples. Sorry about that. Please understand this. ANOVA F scores are very rarely calculated by hand. If you see one, you will do one by hand, and then everything either gets dumped into your TI or it gets dumped into something called SPSS or Minitab, or I think Excel will do. I'm pretty sure it'll do an ANOVA. I'm pretty sure, but it doesn't really matter. We're just for our purposes, we're just using our calculators. And when you get into more advanced techniques of statistical analysis, you're definitely going to see ANOVA. It shows up constantly, and it's a really cool test and a very convenient way to check for differences. All right, so I think that's about it. I think we're about done. And congratulations, you made it through all the material in the textbook. So have a lovely day. Nice job in the course, particularly if you had to watch this, and we'll see you around. Bye.